Okay, so good morning. Let us briefly recap what we have done yesterday. So yesterday we defined the notion of submanifold of Euclidean space. So if V is an n-dimensional Euclidean space and M a subset of V, M is called the smooth d-dimensional manifold, submanifold of V, if for any point in M, I can find an open neighborhood omega x of x in V, some positive real number, and a C-infinite diffeomorphism from omega x to minus eta eta to the n, such that, and I forgot to add this requirement in yesterday, so please write it down. So psi x of x is equal to 0. This is important for to get that. And then we also define the tangent space of M at X as the set of vectors in V, such that there exists a smooth path drawn on the manifold M, such that phi of at time 0 is at X, and the time derivative of phi at 0 is equal to V. Okay. And it's possible to characterize this subspace as the image by this linear map. So that's a derivative of psi x minus 1, so the inverse of this one, at 0, applied to RD times 0. Okay. Okay, and this is, we can see from that it is clearly a d-dimensional vector space. Okay, so geometrically the picture is quite simple. So you have this kind of so it's in this case it's a 2D manifold in the 3D space. Okay, so imagine you have something a surface like that. Okay, and at each point of the surface I can find a neighborhood of the point X, but in R3. Okay, and a 3-dimensional cube, and C-infinity diffeomorphism from this deformed cube. So this is omega x. Huh? This deformed cube is omega x. This is minus eta to the cube here. And psi x is a C-infinity diffeomorphism, which means that psi x is invertible. I can define its inverse. And this map and that one are C-infinity. So infinity many times differentiable with continuous derivatives. Okay? Right. I also defined phi x. So phi x is basically the restriction to psi x to the intersection of the manifold. Yeah. Okay. To the restriction to psi x to the intersection of the manifold and the neighborhood omega x to minus eta eta to the d. So this is called a local chart. And the interesting object is phi x minus 1, because it's a mapping from a flat space, okay, just a rectangle, well, okay, a flat space to the portion of the manifold, which is this one, okay? And so it allows you to work on the manifold using a kind of map, if you want, as if you were in a flat space, okay? Great. And so for I also mentioned the definition of the tangent bundle. So the tangent bundle should be seen as the disjoint union of the tangent space at any point x for x in the manifold, and this should be seen as the submanifold of the product V times V. And so physically, in fact, the elements in this set are in fact the pairs position and velocity. Okay, so you should think of them. Okay, and if xv is in Tm, so this implies that V is necessarily in Txm, okay? By definition of what this is. Okay, good. And so just one quick word about differential calculus on manifolds. So you can give a meaning, yes? Yeah. But we agree that there is not only one B or one X. No, of course not. No, it's any pair of position and velocity, but knowing that you are on a point of the manifold. So the velocity, as you are moving only on the manifold, the velocity must be a vector of the tangent space, okay? Because imagine that you have a dynamical system on the manifold. If you are at point X, you can only move, the velocity can only be a point in Txm, because if it was then the case, the point will leave the manifold, okay? And yeah. Yeah, you can go in any direction, but in the tangent plane. You can not go out of the tangent plane. That's basically what it says, okay? Yeah. Okay, and so this allows you to do differential calculus on manifolds, because now assume that I have a function f which is defined only on the manifold, okay? It is not the restriction of a function defined on the whole space to the manifold, just a function that I define only on the manifold, okay? And assume that it goes from some manifold M to another manifold N, okay? And I would like to talk about derivatives of this function. What does that mean, okay? So I cannot use the definition I was telling you about before, because the definition yesterday was just for, or the day before yesterday, was just for functions defined in a vector space, okay? So the trick to define the derivative or to do a differential calculus when you work on manifolds, so a function defined only on the manifold, is to go through the local chart and the local systems of coordinates, okay? So let's assume that you have a manifold here, M, another manifold here, so this one is 2D, say, this one is 1D, and you have a function from M to N. And to give a meaning of the derivative of f, what you're going to do is to use this local chart and that one, and to work on this function. So this function goes from a vector space R2 here to a vector space R here. And this function is f tilde. So if you want to go from here, first you have to go to the manifold using this. Okay, then you apply f, then you apply this guy. And this is now a manifold defined, a function defined on, okay, maybe it's not exactly eta, but it's a small one, to this one, which is R. Okay, and then you can talk about the differentiability of this one, of this function, okay? And it's possible to prove that, in fact, the differentiability of this function at point 0 here does not depend on the choice of the local chart. So you have something, in fact, intrinsic, okay? And it's a way to do a differential calculus directly on manifold, okay? Right? Okay. Good. So now I think we have all what we need, or almost what we need to, well, there are more in the notes, okay? So I have 30 pages of notes. So I give you more details about all that, but okay. I don't have the time to elaborate more here. Yes? Any differentiation for fiber bundles? Well, I mean, a fiber bundle can be seen as a manifold, so you can apply all that to. But if I want to differentiate, let's say, vector of the fiber, with respect to the
phase one.
Yeah.
It's like it's in one of kind of.
Mm-hmm. Yeah. So, yeah. It's possible to do that using a chart of the local chart for the for the bundle. Yeah, everything fits in this formalism.
Just for the fiber bundles with non-trivial cases.
No, all that is local, okay? So the global thing, the differentiability is local, it's not global. So you
Right. So with this locality, can you get some like a phase change when you go?
Yeah. Well, you can define, for instance, if you are talking about Berry phases. I don't know if it's your point. Yeah. So so the Berry connection will depend on the local charts. Yeah. But if, for instance, you want to integrate the Berry curvature, which is intrinsic, over the manifold, you will find something which does not depend on the chart you used. Okay. So I don't know if it answers your question, but
yeah.
I mean, yeah, you can work locally with these maps, but then if you are after a global object, like a topological invariant, of course, you need to. It's not maybe the best way to go because well, it's necessary if you want to do calculations, but in the end, if you want to think of this object, it's more something global, and you shouldn't see that by going through local chart. Yeah, but this is a bit far from what I wanted to say. Okay, so let's see. Okay, yeah, okay, so now let's talk about first order optimality condition. And start with just comment. So if X is a subset of V, the orthogonal of X, the orthogonal of X is the linear space denoted by X orthogonal, which is a set of Y in V such that for all vector X in V, in X, Y X is equal to 0. So now we have a theorem. So let M be d-dimensional submanifold of an Euclidean space V, and F from V to R, let's say differentiable. And here I add smooth. Then if X star is a minimizer of F on M, then the gradient of F at X star is necessarily orthogonal to the tangent space of 2M at X star. Or equivalently, the gradient with respect to the manifold M at F of X star is equal to 0 where, so what is this guy? So this guy is simply the projection, the orthogonal projection on the space Txm of the gradient of f at point x. So I don't want to, yeah. Yeah, I can erase that. Okay, where again, so the projection, so this is the orthogonal projection on Txm. So let me draw a picture. Okay, it's very simple. So you have your manifold M. If you have a local minimum of f, then the gradient has to be orthogonal to the tangent plane. At x star. Yep.
So I have a question on what came before.
Yeah.
We still have on the manifold that if a function has a differential of 0, it is constant.
Yes, indeed, yes.
And because now you can only study it locally, and when you
Yeah, but that's okay because you can patch everything. Yes.
you have to patch things like continuously, or
No, well, okay. In fact, when you have an atlas, it's more than that because you have a diffeomorphism between and if you have, for instance, if you have some omega x and some omega x prime which overlap, if you so on the intersection, the two are C infinity, and so the map from 1 to the other is also C infinity. So everything is smooth. Okay. Yeah. Okay, so this is a picture that you should keep in mind. Yes? Yeah. Yeah, locally at least, or globally. Yeah, it's yeah, exactly. And so how do you prove that? So the proof is extremely simple, in fact, so I can write it down. The proof is very simple. So what is this space? So this space is simply the space of vectors in V such that sorry, let's V in this tangent space. Then and by definition of the tangent space and phi going from minus tau to V such that phi of t is in M for all t, phi of 0 equal x star, and phi dot of 0 is equal to V. Okay? So we have, because f star is a minimum, we have that f of phi of t is always greater than f of x star, greater or equal, and this is f. Well, you have that. Okay, we have that. Okay, but what's that? For t small, this is I can expand that, Taylor expand phi of t. So phi 0 is x star. Plus t phi dot of 0 is v, plus a little o of t. Okay. So then I use a chain rule, I expand all that, and I find f of x star plus t grad f of x star v plus a little o of t. So this means that this guy is necessarily non-negative for small t, okay? And t can be chosen positive or negative. So this means that this guy has to be 0. Okay? That's the first order. That's the first order variation of f when you move on the manifold M. Okay. And if you get back to the definition of the orthogonal, as you can see that this is true for all V, then this implies that the gradient of f belongs to the orthogonal of this guy. And if I have a vector in the orthogonal of this guy, and if I project it on this guy, well, I find 0. Okay, so this gives you that. Okay, so now we are good. Yes, Hassan. Yes.
Very nice question. Minimizer of f should be independent of what metric you define.
Yes.
Right, but here you have gradients and you also take a projection, and this depends on what you
right. Oh, if you change the metric, you will have exactly the same condition. The fact that yeah.
And then for the second comment, so this proof here, you don't really need the fact that the derivative or the differential exists.
The derivative of what?
The differential of f exists. I mean, you're just taking directional derivatives.
In each direction, yes, that's right. Yeah. But I don't want to bother with that, because for the applications we have, everything is very smooth. So I don't want to everything is smooth here. The stronger results can be obtained by relaxing this assumption, but I mean, it's not the point here. Other questions? Yes?
So simply put, could we say that because x star is a minimizer, the gradient on the manifold has to be 0,
Yeah.
the only non-zero component that remains has to be perpendicular
Yes.
to that manifold.
Yes, exactly. Yeah. Okay, so that's one. And now, so now what do we have to do if we want to for instance, to find the Hartree-Fock equations? Okay, so let's assume that we use the molecular orbital formulation. So what we have to do is to identify the manifold, identify the orthogonal to the tangent space at some point, and compute the gradient for this inner product, and then we just write this equation, okay, or this one, and we will get the equations. Okay, yes? This one? To that one? Yeah, okay, yeah, thank you. Okay, so first you see that I have this greater than that, so I can okay, and then this is true for all t positive, small but positive, and t negative. So if this one is always non-negative for t small and positive and small and negative, it has to be 0. Yeah, t can be negative, absolutely. Yeah. Okay. Right. Okay, so let's write now let's write, let's move to the next part, which is equality constraint optimization problems. And let's revisit the Lagrangian trick. So there is a case where the Lagrangian trick works very well. You just have to add one assumption. So it's the following. So let's do the theorem. Let V, W be Euclidean spaces. And G, C infinity, smooth, such that, no, and V, C infinity. Let, now I define M, which is the set of X in V, such that G of X is equal to 0. And now let's assume that for all X in M, the derivative of G at X, so this is a linear map from V to W, okay, is surjective. Then M is a manifold. Is a manifold is a d-dimensional manifold with d equal n minus m, where this is the dimension of V and this is the dimension of W. Then what we have as well is that we can characterize the tangent space and its orthogonal very easily. So for all X in M, the tangent space to M at X is simply the kernel of dg of X. And the orthogonal of this guy is the orthogonal of the kernel of linear map. And so this is a range of the dual map. So what is the dual map? The adjoint when with the adjoint of the dual map to so this is a map from W to V is the adjoint of dg of X defined by, so you take any V and W in any V in V and any W in W, and you define dg of X star. So this is a map from W to V. So you apply it to W, you obtain a vector in V, and then you take the inner product for V. So here we are, it's an inner product in V. And by definition, this is dgx applied to V, scalar W, but this time we are in W. Yes? Yeah. The kernel? Yes. It's the set of point V. So dg of x, it's a map from V to W. So the kernel is a set of vector V in V such that dgx to V equals 0. Yes. And the range, yes? The range, it's the image in French. OK. OK. Oui, c'est l'image en français. Okay. Yeah. OK. Right? So, noyau, image. So the proof of this theorem is not difficult. It's based on the implicit function theorem. The proof is in the notes. Okay, so I will skip it. I will just comment on it and give you applications. Oops. Okay, so let's see one. So now let VW Euclidean spaces. F from V to R and G from V to W. M, again, is a set of points X in V such that G of X is equal to 0. And we make the same assumption as here. So we assume that for all X in M, the derivative of G of X is surjective. So this implies, of course, that dimension of W is lower or equal to the dimension of V. Okay, so why is that? Then X star is the minimum or minimizer of F on M. So if X star is a minimizer of F1, then there exists a unique lambda star. So this is a Lagrange multiplier. Okay. This Lagrange multiplier lives in W, and such that the gradient of F I point X star is equal to dg X star star applied to lambda star. A lot of stars. Okay. Right. Okay. So that's the first occurrence of the Lagrange multiplier. So second, so now we indeed have a kind of Lagrange principle. So so in addition, X star lambda star is a critical point of the Lagrangian L. So L goes from V to cross W times W in R, and associated to some vector X and Lagrange multiplier lambda, L of X lambda, which is equal to F of X minus lambda g of x. And this is the linear product in W. And perhaps third. So if, yes, there's infinity. Yeah, I forgot to, so G, yeah, now, so let's put times C infinity, okay, it doesn't matter, okay. So then, if now the partial gradient, so if so if the partial Hessian, sorry, so for all V in the tangent space to M at X star, then the second derivative, the partial second derivative of the Lagrangian with respect to L applied, so at this point, and evaluated at V is positive for all V, different from 0. Then X star is a local minimizer. Of F on M. Okay, so this is a second order condition, okay, which is equivalent to the fact that when you minimize a function on R, if the second derivative of F at a critical point is positive, then you are sure that you have a minimizer. Okay. Okay. All right. So let me just give you the proof of the first part. The rest is easy, well, depending on the time. Yeah. Okay, so let me just give you the proof of one on the first assertion. So the proof is extremely simple, okay? We put together what we have so far. So what we know is that X, we know that the gradient of F at X bar, at X star has to be orthogonal to the tangent space, okay? So we know that gradient F of X star is in the tangent space, the orthogonal of the tangent space, and we know that this guy is the range, is the range of dg X star. Okay, so there exists lambda star in W such that grad F of X star is equal to lambda, oh sorry, to dg X star lambda star. And lambda star is unique because this guy is injective just because his adjoint is surjective. Yeah. No, because it's not the same dimension. Yeah, we go from, yeah, because dg X star is surjective. So this is the theorem in full generality in finite dimension. I give you this formulation because if I want to apply it to R34 concham, it's really the way you should write it with Euclidean spaces, because we work with the spaces of matrices. But let me just tell you what's going on if V is equal to Rn and W is equal to Rm. So examples. So if so V is equal to Rn, W is equal to Rm, with M, so lower than N, otherwise it's not very interesting. Then the Lagrangian here is simply f of x minus the usual, well, with the usual Euclidean product, okay, so it's just that. And so if it is f of x minus the sum of lambda I gi of x, okay. So you recover the formula which is in the QChem manual, okay, we're good. If, for instance, V is equal to Rn and W is just R, so then I have a scalar constraint. And no, let me also comment on that. So dg of x in this case, dg of x, it's just a matrix, okay? And so testing if this matrix is surjective means that you just have to check that this matrix has maximal rank, okay? In the sense that, for instance, its column vectors are linearly independent, okay? So checking the surjectivity if you are in Rn or Rm, it's not a big deal, okay? One way to do that is you do an SVD, okay? So you have packages to do that, so it's very easy. You do an SVD and you check that all the singular values are positive, okay? That's all. Okay, so checking this assumption, checking the assumption of the theorem is very easy in practice, okay? That's something important. Because if you have a theorem and you cannot check the assumptions, it's not so good, okay? So here it's easy on a practical case to check the assumptions, okay? So it's easy to know if you are able, if you are allowed, sorry, to use a Lagrangian trick or not. Okay, second case. So now if V is equal to Rn and W is equal to R, there is a very simple interpretation of that in terms of level sets. So what is M in this case? So in this case, so M is a n-1 dimensional manifold. So it's called an hypersurface, okay? It's an hypersurface. So let me draw a picture in 2D. So let's say in the picture, I will take n equal 2 and m and r. So in this case, this is M, okay? So it's a smooth curve, okay? And I want to minimize a function f. So assume that, for instance, now I'm drawing the level sets of f, okay? So let's assume that the absolute minimum of f is here, okay? For instance, f is equal to 0 here, and then maybe 1/10 here. Then these are the level sets. Then it can go crazy, okay, it can do something like that. And so on. Okay, maybe my picture is not so good. Okay, but in this case, where is the minimizer of M of F when I work on the manifold? Okay, so if the absolute minimum of F is here, so let's say that here it's 0, it's 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, okay? And you can see that the minimum of F is attained at this point, okay? Right? So at this point, the gradient is indeed, so the gradient is always perpendicular to the level set, okay? Because on a level set, the function is constant. So the gradient has to be perpendicular, orthogonal to the level set, okay? So the gradient of F is like that, because it is orthogonal to the yellow level set, and it points towards the ascent direction. This is X star here. But then you can see as well that the gradient of G, because M is G minus 1 of 0, so it's also level set, okay? So the gradient of G has to be orthogonal to this line. So the gradient is perhaps like that. Okay. And so what's going on? You have two vectors which are orthogonals to two tangent planes, to say, which are tangent. Okay. And so necessarily these two guys are collinear. And as one of them is non-zero, because we know that by assumption, this is by assumption the dg is surjective, so this means that the gradient of g is not zero. So if I have two collinear vectors and one of them is not zero, I can always write the other one as lambda times this one. And it's unique, because, well, there is a unique way to write that, okay? So this is the interpretation of the Lagrange multiplier, okay? So it's not something completely out of the blue, okay? It's not coming out of the blue. Yes? Yeah. That's the level sets of F. That's the set of F, yes. So the white one is a manifold. It turns out that it is also a level set. Yeah.
But I don't understand the minimum you pointed to the
No, because this one, so my manifold is just this. And the minimum of F on the manifold is this point. Because then on other points, the value is lower, is higher. Okay, because. Yeah.
The tangent of F is perpendicular to the yellow.
Yeah,
and the tangent of G is perpendicular to the white.
Yeah, but the two are tangent. They are tangent because otherwise, if they were not, like here, I could lower the value by going in the, yeah, they must be tangent, okay? Yeah. So geometrically is the picture, okay? If the level sets are not tangent, so let's say I'm here, I can lower the value of F and still stay on the manifold. The only way I cannot do that is when the two level sets are tangent, okay? Okay, some remark now. Another remark is that X star lambda star is not a minimizer of X star of L in general, it is only a critical point. In fact, a saddle point. So let's take the example when I am in the second condition. So assume the condition, the third condition is satisfied. So then the full Hessian of the Lagrangian is as follows. So the full Hessian of the Lagrangian, so this one depends on at x star lambda star. So it's the part relative to x star, so that's the second derivative with respect to x of the Lagrangian. Okay. Then the second derivative of the Lagrangian with respect to lambda, but this is 0, okay, because the Lagrangian is linear in lambda. Okay, so it's 0. And then I have to put dgx here and dg of x, so star here. So I assume that here I assume that v equal r n and w equal rm. Okay. So this matrix is of the form A B transpose B 0 with A positive definite and B surjective or maximal rank. Then it is an exercise of linear algebra. You should do it if you don't know the result, because it's a nice exercise based on the min-max principle. Then this matrix has exactly m positive eigenvalues and n and m negative eigenvalues. Okay. Then L, sorry, is the second derivative of L. So the Hessian matrix, okay? So it's a Hessian matrix of size m plus n times n plus m, and it's symmetric as n positive eigenvalues and m negative eigenvalues. So this is really a saddle point, okay? Something like that. Okay? Like a saddle. Okay, at this point, you have something like that. Okay, you are like that in some direction and like that in other directions. Yes?
Maybe I missed something. What's the meaning of this space that you put with lambda? Here we were just looking at the space.
Yeah, absolutely. This is in real space.
Right now on the left.
Yeah.
It's in the space.
So here, yeah, here I mean, it's like x and lambda.
Yeah, so it's like this one is
Yeah, yeah. Perhaps, but I'm not sure. Yeah. Yeah.
If you are on the saddle point for F.
No. Okay. Yeah.
Do you still have the fact that all the eigenvalues related to lambda are negative?
No. Not the, let's see. Oh, you mean that you have more eigenvalues?
Well, so for example, I am on a saddle point for, so let's say that A
Yeah.
has a negative eigenvalue.
Okay, yeah, I see. So let's assume that this one, for instance, n minus 1 positive and 1 negative eigenvalues. Yeah, I think in this case you have, I should check, but I think, yeah, I would say that you have n-1 positive and n+1 negative, but I'm not completely sure, but that would be what I think. Yeah.
Maybe I have a question really. If you have all positive eigenvalues?
No.
In general?
No. It's already if you have the generic case, but forget about that. Okay. Yeah. Exactly. For instance, as soon as this one satisfies the second order optimality condition, then you're sure that you have n positive and n negative. Okay. Right? Okay. So you never minimize Lagrangians. Okay. In the best case scenario, you're looking for saddle points. Okay. So it's a min-max problem. Okay. Good. So now it's time to derive the Hartree-Fock equations. So of course, in usual quantum chemistry courses, you don't need 4 hours plus to derive the Hartree-Fock equations, but it's just because I wanted to set up the formalism. But once you have the formalism, then it's very easy to derive the Hartree-Fock equations. Okay. So that's 3.3.3.2. Optimization on generalized Stiefel manifolds. So let's consider M equal to the set of matrices C. So I'm sticking to the notation I introduced at the very beginning. So that's the matrix of molecular orbital coefficients in the atomic orbital basis set. And you want this constraint to be satisfied where S is a matrix of size NB times NB, symmetric, and positive definite. So this is the overlap matrix. Okay. So this is called the generalized Stiefel manifold because in the special case where S is the identity, it is exactly the Stiefel manifold, which is a well-known object in differential geometry. So let's prove that it is a manifold. Theorem. Yeah. Thank you. Yes, NB. Thanks. So theorem M is a d-dimensional smooth d-dimensional submanifold of R NB times N with D. So what is a dimension? It's NB N minus N+1 over 2. That's the number of independent degrees of freedom, if you want. So to prove it, we will use the submersion theorem. So the theorem I stated at the beginning. So let V equal R NB times N and W R N times N symmetric. Now G is a function from V to W, which associates to some matrix C, the matrix G of C, defined as C transpose SC minus identity. So if I remember well, we already computed the derivative of this map. So the derivative of G at C applied to some vector, let me call it X, is X transpose SC plus C transpose SX. Okay, so computation we have already done, so quite obvious. Okay, so now we need to prove that this map is surjective. So we need to find for any y in W a matrix Z in V such that dgc of V is equal to W to Y. So let's Y in W. So it's a symmetric n by n matrix. And so what can I take for X? We have, what we want is that. Huh? Okay. If I can find what's there, then I'm good, because this will prove that this map is surjective. Okay, that's the definition of surjectivity. So what can I take? Yeah, so no, but assume I just have this, okay? What should I take? I know that, yeah, C, oh, sorry, it's for C in M, okay? So C is in M, meaning that we have this equality. Okay, yes, so I should take Cy, but because of that, I take half of Cy. Okay, and then you can check that if you take this X here, so you have half of C transpose SC, which is identity Y, and here I transpose everything. Y is a symmetric matrix. When I transpose it, I still get Y. So it's half YC transpose, and then, okay, and you're good. Okay, so then I have that. Therefore, dg of C is surjective for all C in M. And then hence, so M equal the set of points C in V such that G of C is equal to 0 is a d-dimensional manifold with D equal, so the dimension of V minus the dimension of W. So the dimension of V is just the product of these two guys. And the dimension of W, so we have n by n, but symmetric matrices. So I have entries which correspond. And so the dimension is n plus 1 divided by 2. Okay? Okay, great. So now what do we have to do? To apply, to derive the R-Trifort equation, I have to compute the adjoint of the GC, okay? Because the adjoint is what I need to apply the Lagrange multiplier trick, okay? So let C in M And let us compute the adjoint of DGC, okay? So what is the adjoint of DGC? The adjoint of DGC is the map of DGC star. So this is a map from V, from W to V, defined by, so for all, so C in V, and let's call it lambda in W. C BGC star lambda. So here, this is an inner product in W, in V, is equal to BGC, sorry, it's not C here, it's, let's call it V, X. DGC X lambda. Yeah. Okay. So what's that? So here we use simply the okay. So let's do this way. So this we know what it is. It is X star C X star SC plus C star SX lambda. So here we use a Frobenius inner product. Okay, so this is just the trace of these are all symmetric matrices, so I don't need to bother to transpose the matrix. Just that, right? And so I use, as previously, I use linearity of the trace. I use trace of A transpose equals trace of A, the cyclicity condition and cyclicity property and so on. And then after some work, but it's not big work, I find that. Okay, so this one obviously gives that, and then when I transpose and I use cyclicity, I find that. Okay, and therefore you can see. So this is also the Frobenius product, and this is X to SC lambda. Okay, and so thus VGC star lambda is equal to 2SC lambda. Okay, and this looks familiar for people who know our three-fork theory. Yeah, more or less.
In chemistry, we often like to write the derivatives with respect to C star.
Yeah.
Assuming the coefficients are complex, and so this is the correct way of writing this.
Yeah, that's a way to write that. Yes, yes. And it sticks to the geometry. You don't need to introduce a Lagrange multiplier, which comes out of the blue and so on. It's just you apply. We are still using this very simple picture. Okay. Yeah, but I mean, geometrically, it's just that. We just apply that. We just have to compute what is, and now we use the fact that f of X star. So if we go back to the R3 problem. So, and so, should I talk about that now or later? Yeah, so let's talk about that now. So what is R threefold? Understand it. I have 15 minutes? Okay. Let's go back to R threefold. So R threefold is a minimizer of E of C with C in R and B times N and C transpose SC equal identity. Okay, so I can see that as the infimum for C in M of the function E of C. Okay. So the criticality condition is there exists some lambda, well, is just that. So C is in T, C M orthogonal. This is the range of D, G, C star. And therefore, because I know what is D, G, C star, and then it gives me gradient f of C equal to C S lambda for some lambda square matrix symmetric square matrix, n by n square matrix.
The function f is E. Yeah.
Yes, thank you. It's E. Thank you. And now what I just have to do is to compute this gradient. So what is this function? This function is curly E of CC transpose, where curly E in R threefold, it's the trace of HD plus half the trace of G of D, okay, with the notation in quantum chemistry textbooks. I think that's a usual notation. Okay, fine. Okay. So let me compute the gradient of this one. So to compute the gradient, as usual, you first compute the derivative. So you make a small variation of C. So this is E of C plus X transpose. And this is E of C transpose plus C X transpose plus X transpose, sorry, C plus X, C transpose plus little o of X. And so this is E of curly E of CC transpose, but this is E of C, plus the gradient of E at CC transpose applied, so scalar, this guy. Right? Plus something small. This gradient is, in fact, I should write it like that. Okay. So then what is this guy? It's E of C plus the trace of, so this matrix, I will call it F of CC transpose. For some reason, we will see. Okay. Okay, it's F of CC transpose. So what's that? It's F of CC transpose. We are dealing with symmetric matrix, so it's just CX transpose plus X C transpose plus little o of X. And using always the same trick is I split this into, I use a trace of A transport equal trace of A and the cyclicity of the trace. I find that this is a trace of X transpose of F of C transpose C transpose X with a factor 2 here. And that I can write it as 2 F CC transpose C X. And this time I mean V. And therefore, the gradient of E at point C is 2 F CC transpose C. And therefore, the Hartree-Fock equations, so the Hartree-Fock equations, the criticality equation, these are the Hartree-Fock equations, read. So I put together this and this, and I obtain F of CC transpose C equal SC lambda. Okay. Now I just have to check that the F is in fact the Fock matrix, okay? But this is easy because what is that? This is the gradient of E, okay? And the gradient of E finally, using the fact that G has some properties, so the tensor G here has some properties, and the properties is that trace of G D prime equal trace of G D prime D. So this is due to the symmetry of the electronic integrals, okay? We have. So I remember that I think at least well, the gradient of this term is pretty clear because this is already an inner product, okay? The gradient of this term is H, and then when you do the math, you find that the gradient, that the Fock matrix of D, which is a gradient of E of D, is equal to H plus G of D. And that's the Fock matrix. And you're done, okay? So this gives you a purely geometrical derivation of the Hartree-Fock equation. I did not introduce some Lagrange multiplier, which is a weird object, okay? I just use the fact that when you minimize the function of the manifold, we have this picture. Okay, that's all. Okay? So the only thing is, if you understand this picture, then it's just linear algebra. You just have to, to compute the gradient of E, okay, and identify. This is more important. The orthogonal to the tangent plane of the manifold. But I mean, this is just some algebra. Okay. Yes.
Like when you check the stability of your Hartree-Fock
Yes.
solution,
Uh-huh.
the fact that you end up with a linear response type of
Yes.
organization is basically due to this.
Yes. 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 It's the second order condition that I wrote. Yes, it's related to that. Yes. So
you can derive that purely.
yeah, sure. Yeah. It's exactly. It's the second. Yeah, I don't have the time, but maybe next time I can explain why, if you have these conditions, then you are sure that you have a local. It's not difficult. You just have to expand at the second order F and G, and yeah. Yes. Yeah. Yeah. No. E and G are defined on the whole matrix spaces. So now let me comment on this point. So I take V equal R NB times N. So this is a vector space. W is R, N times N symmetric. This is also a vector space. Then E is defined from V to R, and G is defined from V to W. Okay, in the definition of G and F, yeah, look, this is a definition of E. Okay, and you can see that you can apply that to any matrix C. Okay, you don't need it to be on the manifold. Okay, this is important to get this picture here. Yeah, the derivative is a map dg at point C is from V to W for any C in V. But if C belongs to the manifold, then this guy is surjective. Okay?
I can't understand is that early in your lecture,
Yeah.
it took a long time to show us that the derivative on the manifold is quite complicated. You have a sort of
Yeah, but here I don't use the derivative on the manifold. I use the derivative on the whole space. Yeah. Okay. Yes, it's a criticality condition. It's the same as when you minimize a function, or it gives you these points. Okay, it's the best you can do. What you check is the first order variation of f when you move around is 0. That's all what it tells you. And the third condition in my theorem tells you that if the second derivative of the Lagrangian with respect only to the x variable, if this guy is positive definite, then you have a local minimum. Okay.
Where do you need the C infinity?
Well, short answer, nowhere. Second answer is for the manifold, it's good to have something smooth, because then you can handle any kind of problem, not only this one. So that's why when your manifold is smooth, you should say it. Okay, and it turns out that in quantum chemistry, the manifolds are always smooth. Okay, for the function, it's different, because for the function, so here it turns out that the Hartree-Fock functional is polynomial, so it's C infinity. For Kohn-Sham, it's a bit painful because, for instance, at the continuous level, the LDA functional is not C infinity. Okay, because at some point you have this, and so if you derive too many times, and if rho is very small, you're in trouble. Okay, so in DFT, it's not C infinity. However, it is differentiable, and this is enough to derive the equations. Okay.
Just to bounce, we did so the Leibniz constant search.
Yeah.
Can you see that exactly in that framework, or is there some differences with this?
There is a big, well, let's see, the constraint search. So you mean when you minimize over rho, and then you minimize on the side which gives rho?
Yes.
And you go, okay. This guy. So first here the set is the set on which you minimize. So it's not a manifold, okay? It's a set of function rho which are integrable, positive, and such that the square root of rho is in H1 space. Okay, so this is a convex set, but it's not. It's a convex set, but it's not a manifold. Okay, so here it's more in the framework of convex optimization.
Because when you look for the functional, you actually look, so you minimize t plus b.
Yeah.
For all the psi that give rho. So you have a constraint on psi because it has to be rho.
Yes, correct.
And so you have to introduce.
Oh, you mean for a given rho, what is the set of sides?
And so that this you can recast that as.
Perhaps, yeah. So you mean it's for this problem, no, not this one. Okay. For this problem, yeah, maybe.
That ensure that the density.
Yeah, I see your point. Yeah.
in this so that.
Yeah.
Because, so why are you, in that case, able to recast that as lead convex formulation? So what is
The trick to
Yes.
oh, the trick is very simple. Is to say, okay, instead of that, at the very beginning. Oops. At the very beginning, you say that minimizing, so the ground state is given by that. Okay, but it's also the trace of H gamma for n-body density matrices which satisfy that. Okay, and this is convex, this is linear and it's convex, and so the problem is convex from the very beginning. Yes, yes, and then you do you do that, but instead of rho, you say gamma. And then it's convex.
But you could say, I'm gonna write like a Lagrange multiplier where I transform.
But Lagrange multiplier, you have to, because here you are in infinite dimension. Okay, so checking everything is probably more complicated.
Okay. But if I'm very naive, then I could.
Yeah.
The potential as a Lagrange multiplier.
Yeah, but then you have the problem of V representability is exactly related to that. Okay, so the good person to work on that is Simen Kval, the people in Norway. So their way is to regularize the density, well, the problem, yeah, and then do a formulation for a regularized problem. Okay, yes?
So here you show that the Hartree solution C is only a saddle point for the.
Yeah. Yes. Well, yeah, that's right. Yeah. Okay. Go on, because
I just want to ask so about the number of negative eigenvalues.
yes. Okay. So very interesting question. Okay. So this is the criticality conditions for Hartree-Fock. Okay. You can do better because for Hartree-Fock, so first you know that you can diagonalize lambda, blah blah blah. So that and then you have the usual representation of the Hartree-Fock equation, and then you can prove that. So if you diagonalize lambda, basically you find equations which are like that, okay? And I and the phi I are orthogonal, and D is the sum of phi I transpose. Okay, so it's what you get. It turns out that for Hartree-Fock, you know that if D is a minimizer, then the epsilon I are the lowest negative eigenvalues, and there is a gap between the HOMO and the LUMO, positive gap, always for Hartree-Fock. Okay. This is not, and if you don't put spin constraints for restricted Hartree-Fock, I'm not sure it's true. For unrestricted or for generalized Hartree-Fock, it's true. For Concham, I think it's an open problem. Yeah.
That's where you need it.
Yeah, sadly. Yeah. Well, for Hartree-Fock, you need it as well. I mean, if you want to do MP2.
Don't break fortunately, so we have to make
All right. Okay. Fair enough. Okay. So I think it's time for lunch. So thank you for your attention.